This is a problem on the uncertainty principle, and it reads: particles pass through a single slit of width 0.200 millimeters. The de Broglie wavelength of each particle is 633 nanometers. After the particles pass through the slit, they spread out over a range of angles. Use the Heisenberg uncertainty principle to determine the minimum range of angles. Okay, I'm just going to go to Physics Educational Technologies, FET, and again, this is through quantum physics, and so that's where I get this particular applet, and then I click on a few things and I choose electrons, and I have a double slit. I know the problem says single slit, but just using here a double slit in order to show that despite of the electrons making a bright part on the screen here and the bright part on the screen here, they actually make bright parts in several places, here, 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 and if we had more space we would see them further out as well, because for this double slit experiment for electrons the wave nature of electrons applies. And then this particular problem is about, well, for a given slit width, how large in degrees is the brightness on the screen, and that is to be determined by the uncertainty principle, which we can see. This is a picture from the book, and so is this. There's a picture from the book as well, that we can see. Well, here we have the delta momentum, the uncertainty in the momentum, and here we just have the forward momentum going up here, and here we have the width of the slit, and that also determines the uncertainty in the position. So using the uncertainty principle, this can be written as follows. So delta Py times delta y is larger or equal to Planck's constant divided by 4 pi, and I got that from the book. A little more space, and as I said a moment ago, for the uncertainty in the y position, we're using the width of the slit. I personally don't like the capital W because it looks like work to me, but they're using capital W here for the width of the slit. And then in order to get a true result, I change the larger than to an equal, so we come actually up with a number. Okay, and as we can see, things are given here. Delta Py equals h over 4 pi w. Well, then I'm supposed to figure out what the angle is. Well, I look at this diagram here. The angle for this kind of triangle is going to be the tangent of delta Py over Px. So the tangent of the opposite, which is delta Py, divided by the adjacent, which is Px. So theta, tangent theta, equals what I just said a moment ago. So in order to solve for theta, I of course take the inverse tangent, and I'm going to plug in this expression here for delta Py with everything else given, but I also have to figure out what Px is, and that's where the de Broglie wavelength comes in, so that lambda equals h over Px, and that's what I plug in. Just going to change the color here for a moment. So this one will be plugged in here, this will be plugged in here, and then let's see, oh yeah, and the tangent goes to the other side, so that we're going to come up with theta equals inverse tangent of, let's see, try not to make a mistake here as I plug in numbers, and try not to cough before I turn the microphone off, which fortunately I did. So delta py here is going to be h over 4 pi and the width, and then I plug in the px, which is going to be h over lambda, respectively. The lambda goes to the numerator, and then it turns out that Planck's constant actually divides out, and now at that point all that needs to be done is plug in the de Broglie wavelength, which is given as 0.200 millimeters and 633 nanometers, and the width, which is given as 0.200 millimeters. So this one here, 0.200 millimeters, and this one here would be 633 nanometers, but we would have to have the same units here, and of course 633 nanometers is 0.00633 millimeters, because from nanometers to millimeters I need to shift the decimal point 6 times. Notice that there's a really tiny number in the numerator divided by 4 pi and by 0.200, which means the angle is going to come out to a pretty small number in degrees. Now I got done with the problem here, but I wanted to say a couple of things about Heisenberg's uncertainty principle. So delta P times delta X is larger or equal to Planck's constant, that was supposed to be h, divided by 4 pi, respectively, the uncertainty in the energy times the uncertainty in the time, same expression, larger or equal to Planck's constant, divided by 4 pi. And that means if we try to measure the position of a particle to a certain accuracy, then the accuracy of the momentum has to be at least that much that it satisfies this expression. Or if we try to determine the energy, the kinetic energy of a particle very accurately, where we have a certain inaccuracy in it, then the time can only be known that accurate that it satisfies this expression. Or in other words, neither the momentum nor the position of a particle can be known exactly. There is some kind of little spread. This particular problem here was about the spread in an angle, where I used the uncertainty principle for that. The uncertainty principle comes in handy for certain things. For example, for the alpha decay of particles, and let me just move this down here that we can see the copyright release. Imagine that this alpha particle here, which is nothing but a helium atom nucleus, is trying to penetrate into this huge nucleus, which may be a thorium nucleus, and when it penetrates in there it becomes uranium because of the addition of the 2 protons inside the helium nucleus. Well, in order to do so, it would have to overcome the electromagnetic repulsion, because there are 2 protons here and there are 90 protons here, and of course there's a huge Coulomb force, repelling Coulomb force between the 2 particles. It has to overcome that. If it has enough energy, it could do that. However, it actually doesn't, but it still can get in there, and that's what's called a tunnel effect. Now, I might have mentioned alpha decay, which is radioactive decay. The alpha particle, the helium nucleus, is actually going the opposite direction. It's actually going out from a uranium nucleus, and then as it goes out, it leaves behind a thorium nucleus because that one lost 2 protons. However, the phenomenon is still the same. It doesn't have enough energy to get out, but we still see it, and that's where tunneling comes in. This is from hyperphysics, and we can see the copyright here. And here in what's called the tunnel effect for alpha decay, we have the particle inside the nucleus, and then outside the nucleus we see the Coulomb barrier here, this kind of hyperbola shape because it goes with 1 over the distance squared, and the energy of the helium nucleus is not large enough to overcome that barrier. However, we do see that alpha decay, we do see the helium nucleus outside, and we know that that helium nucleus, because it's very fast, has a high kinetic energy, is very dangerous to us. So we don't want to be around radioactive materials sending out alpha radiation or beta or gamma. But it still is able to penetrate that barrier here. It's called a tunnel effect. And for a short enough distance, if we call this one here delta x, then there is a certain uncertainty. So, there is a certain inaccuracy of the momentum there that it actually has enough momentum to tunnel through, or so to say jump over, resulting in a certain probability that it will actually get out. Or if we talk about that, if it takes a short enough time here, then it has enough inaccuracy, uncertainty in the energy that it actually can penetrate through here, or again climb over here. So either one of those two uncertainty principles, ways of writing them down, can be used. So a tunnel effect would be one of them. Another one is the white dwarf, and I just pulled this image here. This is a Hubble photo, which are all copyright free. So this one here is Sirius A, the brightest star that we can see in the sky, but this little blink down there is Sirius B, which is orbiting Sirius A, and it's not that this star here is a whole lot bigger than that little star down there. It is quite a bit bigger, but not that much. This is just an optical effect. Also notice these spikes here, they actually come from the telescope, the stress in the telescope, and these here are airy rings that produce an image that is much larger than it really is. Probably Sirius about this size here, and even this little one here is a little overexposed. In any case, this one is much brighter than this one here. Sirius B is called a white dwarf, and that white dwarf, I have to scroll down a little bit, is about the size of Earth or a little smaller, and therefore it has a huge density. And in the white dwarf, all electrons, it's hot enough that all electrons are removed from the remaining nuclei, which are mostly carbon. So this is very high pressurized, very hot, pure carbon, which we could think of as a huge diamond the size of Earth. That's what a white dwarf is. And it is being held against gravity by what's called electron degeneracy, where the electrons are the ones that are exerting the pressure against gravity, and that is governed by the uncertainty principle and the Pauli exclusion principle. And the uncertainty principle means that in a certain volume there can be only two, that's a Pauli exclusion principle with the spin up and spin down, that there can be only two electrons within a given delta V, given delta volume of momentum times the uncertainty in the distance. So overall, the uncertainty principle governs that a white dwarf can actually exist, and of course we can observe those white dwarfs. This problem says, in a Rutherford scattering experiment, a target nucleus has a diameter of 1.4 times 10 to the negative 14 meters. The incoming alpha particle has a mass of 6.64 times 10 to the negative 27 kilograms. What is the kinetic energy of an alpha particle that has a de Broglie wavelength equal to the diameter of the target nucleus? Ignore relativistic effects. So first of all, about Rutherford scattering. So there's a source of alpha particles, high energetic helium nuclei that are hitting a gold foil, and then they spread out here, and you can figure out on the screen here where they're hitting as they're being deflected inside the gold foil. Well, around the time that Rutherford made his experiment in the early 20th century, this one here is from Hyperphysics, this was the model of the atom, that if this is the atom here, then there would be the electrons throughout here, and they would be kind of like a charge cloud, a positive charge cloud around here. So when a alpha particle is being sent through, it would be deflected, and if I click forward here, then, or respectively here, if I click model of the small deflection angle, then we would come up with here this tiny angle 0.02 degrees that it would be deflected according to this charge cloud. This was before it was known that the atom is actually made up of a tiny nucleus with the electron being floating around in orbits around it, rather than having this Thom's model or plum pudding model. So here what would be expected if it was this plum pudding model, that the alpha would be hitting right here in the back with a tiny deflection angle, so it would only hit here. Instead, what Rutherford observed is it just hit about everywhere, because the atom does not look like that. Electrons within this blob of positive charge, but instead it was a, let's see, where do I find this one here? Here, target nucleus with the electrons way out here, and the alpha particle would be deflected under quite some large angle because it's able to get relatively close. On from physics educational technologies, again quantum physics, and then click on actually Rutherford scattering. This would be the old model, the plum pudding model, and if I turn on these alpha particles, then they're going pretty straight through this, all these plum pudding atoms that are sitting around here with the electrons scattered throughout, and nothing is happening really, because the negative and the positive charges between electrons and the nucleus are canceling each other. But instead, this is the way it looks like. Here's the nucleus, and the electrons are way out here, and if the alpha particles come relatively close to the nucleus, they are still, of course, are being deflected by the Coulomb force in all kinds of directions. Such as showing here. Okay, let's do the calculation. They want us to figure out what the kinetic energy is. And Ke is given as 1/2 mass times velocity squared. They also tell us that the target nucleus has a diameter of 1.4 times 10 to the negative 14 meters. So I'm going to write that down. D equals 1.4 times 10 to the negative 14 meters. If I can. And they say that was the kinetic energy of an alpha particle that has a de Broglie wavelength equal to the diameter of the target nucleus. So lambda equals d. Now, for the de Broglie wavelength, we know this expression, lambda equals Planck's constant over the momentum. So pretty much we have to figure this one out, and this one here is given. All we have to do is plug this in here and come up with what the momentum is. But then what are we going to do with it? Well, we go way back and see that the momentum is mass times velocity, and then we can see, oh, perhaps we can plug that in here between these two equations. And I'm going to do a little bit of algebra. Notice this one here, Ke equals, and I'm going to put mv squared on the above the fraction bar in the numerator and the 2 down here, same expression, but now watch this here. I'm going to multiply this with m mass in the numerator and in the denominator. Of course, nothing has changed, but the way I look at it here now is that I have mv squared, which would mean the momentum squared. So I'm going to write this one down. Kinetic energy equals momentum squared divided by 2m, as long as it's non-relativistic. Then it looks a little bit different. This one is a typical expression between kinetic energy and the momentum of a particle. Kinetic energy equals momentum squared divided by twice the mass. And now all I have to do is take this expression, plug it in here. So Ke equals Planck's constant squared divided by twice the mass, and the de Broglie wavelength squared equals, and if we keep everything in standard units, so lambda is given in meters, mass is given in kilograms. Of course, the given 6.64 times 10 to the negative 27 kilograms comes from 4 times the atomic mass unit. Respectively, it's a little bit lower than that because of the binding energy. But in any case, it's given as in kilograms. This is given in meters. This one is in standard units. So kinetic energy also comes out in joules. Okay, a couple more things. For one, in the problem, it says that to ignore relativistic effects. So let me show you that that is justified. So in order to calculate the velocity, in order to say actually that the speed of the alpha particle is small enough compared to the speed of light that relativistic effects can be neglected, what I'm going to compute is the momentum, which is Planck's constant, divided by the given de Broglie wavelength, so that's the mass, I'm sorry, that's the momentum of the particle, and then I divide that by the mass, which is given in the problem. And I come up with 7 million meters per second compared to the speed of light of 300 million meters per second. You know, it's approximately 2% of it. But then, of course, as far as the relativistic formula is concerned, it goes into the 1 over square root of 1 minus v squared over c squared. So I'm going to plug it in that one. And of course, we already can see that, you know, it's relatively small compared to the speed of light. Only 2% of it. But let me plug it in anyway to the relativistic formula, which would tell us what the mass increase is, and the mass increase is only as 0.028%. And then we can really say, yeah, you know, let's just leave it this way here. We're going to be accurate to only 2 significant figures anyway, and the relativistic effect shows up in the 4th figure. So that's why they say ignore relativistic effects. Okay, one more thing here, just to show the copyright free for this image, that here we have this plum pudding model, we have the atom with the electrons throughout here, and then kind of like a blob of positive charge, and the particle should just go through because the negative and charges and the positive charges neutralize each other. But what really happens is that the nucleus with the positive charges here and the electrons are around here, and so sure, the helium nucleus, the incoming alpha particle, does feel the electron charges, but then once it's inside the atom, it only sees the nucleus, and it may be deflected like this, or it may be shot back. And there's a quote from Ernest Rutherford, and he said, "It is quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." And so on. So, of course, this was early 20th century, pre-World War I, so they used 15-inch shells for artillery. And so, yeah, just to quote it again, he said that it's as if you shoot a cannonball at a piece of tissue paper, and instead of going through, the cannonball is coming right back at you.